Welcome to the second session, where we shift gears to some extent. Where the first session was focusing on observations and mechanisms. And this is something which is mostly in the realm of natural science. We now start to approach the interface and into the interface between natural science and social science, because we go into detection and prediction, and one of the hypotheses is that if you want to think about detection and prediction, you have to think about the decision-making needs. And so here we start to come into this interface. This afternoon, we have a short introduction by myself, which will be over hopefully soon. And then we have Hans von Storch, who gives a talk about, I hope, the reconstructing past climate from noisy data, implications for climate change detection. We then have a barbecue tonight, and we will reconvene tomorrow at 3 o'clock with Hernan Garcia et al. And then we go on. And so I thought in this talk here, we go a little bit more into detail, and I wanted to give a broad outline what I think are key challenges that the field is right now facing, and also suggest not just challenges, but also a few approaches to address at least one or two of those challenges. And for me, it always helps to draw a simple diagram to see where we are and what the problems are. And the point is that if you want to have a sound strategy of risk management in the face of uncertain climate thresholds, you face actually two challenges on a very broad scale. One, you need fundamental advances in the disciplines. This is not just oceanography or numerical modeling or statistics. Also, you have to know how decision makers make decisions under deep uncertainty, or how to optimize an observation system. This also brings us to the second challenge, that the real system could be seen as a feedback loop, which is iterated over time, and you're actually looking at a coupled natural human system. This is why we have the problem. And that if you want to analyze it, you have to look at a coupled natural human system. In the same way that you cannot model an MOC with an ocean-only model, you need the ocean atmosphere feedback. You might have to look at the coupled system if you want to look at this problem. The second and a nice point to it, I think, is that there are some questions which fall squarely within natural science. So, for example, how sensitive are the thresholds to forcing, which is what we have heard talks mostly about in the first session. If you go then into this next question, if you assume you have some knowledge about this, with some uncertainty, then the next question might be, would we have enough warning time? Would we see it coming? So this is either the anvil falling down on Wile E. Coyote, or going over a waterfall, or trying to get off an exit and you have just missed a sign, which a picture I attributed to, a very nice picture, I like that. But note here, enough is a very difficult word. Because it means enough for what? Enough for decision making, enough for having wrong confidence excluded. And so you have entered into the realm of fields that, when you're trained as a natural scientist, is sometimes a little bit iffy, because you, from my point of view, just the entering. Once you're in there, it gets better. You have to think about ethics, psychology, economics, or even operations research. You can go then into the question, well, if you think you are in a situation like Wile E. Coyote and you want to have an improved warning system, then how do you do that? And once you have different options, the question is, which option should you choose? Which is a question that then becomes more into the field of economics and psychology and ethics. But once you've chosen a strategy, you have changed, presumably, the forcing, and you have to play the entire game again, because the sensitivity of the thresholds depend on the time history of forcing. And so that's, I think, one conceptual way how to think about the organization of this workshop that we have spent. And I've been accused of linear thinking by a few in the room. That I start with, get the mechanisms right, think about detection, think about prediction, make decisions, stop. And I said, well, I might be linear thinking, but at least I'm twisted, and I'm looking about to interactions. And so I think this might be one way. this makes you happy.
What does threshold mean?
We will have this in the discussion. No, threshold, if you had been here at the first talk, we have discussed it. No.
Decision-making thresholds or climatic thresholds?
No, with threshold I refer to the location where predominantly negative feedback changes to a positive feedback, predominantly where the response gets faster than the forcing. So it is a threshold very close and akin to your definition this morning, and I don't want to flip back the flipboards.
Okay, so it's physical.
Physical threshold. There might be other thresholds in there. This is just a cartoon depiction trying to have the essence of it. Okay, so why is this important? Why do we care? And here, true to George Philander, sometimes maybe the younger generation hasn't seen the golden age when science was done just for the sake of beauty and insight. I was starting out at this actually as a term project at Princeton University in a class on policy science interactions with Frank von Hippel, and I said, oh, this is a wonderful little project for a class. This was 6 years ago. And this is the paper that came out of this class, published 2004, so you see that one is slightly overconfident in planning. And this is a simple economic model, pretty much run-of-the-mill, using Nordhaus 1994, the DICE model, which I've talked about. And what we analyze here are optimal abatement levels. So those are optimal in order to maximize some function of per capita consumption over time, under uncertainty in learning compared to certainty. And this is for a specific case when you put into this DICE model a representation of the MOC, you assume Stocker and Schmittner is 100% right, the 1997 paper. You put this in, you get critical CO2 levels, you have to start below. And if you're certain and you have a certain damage, which is actually not catastrophic, around 3% of GDP, then the economic model says, well, we don't want to go there because it's cheaper to avoid it than crossing it, which is an interesting number in itself, because reasonable, some would say maybe too large, but estimates of damages that are much less order of magnitude than what has been said before is catastrophic, at least one order of magnitude, give you an increase in optimal abatement, which is the reduction of CO2 compared to business as usual. This is if you have no uncertainty. In contrast, if you're uncertain here just about one parameter, the climate sensitivity, and this is 3.4 degree, and then using some IPCC numbers to get an equally likely sample, and you know that you will learn by 2075, you have an interesting behavior of the model. You actually do less until you learn, and then you revisit the question, and if you learn that the red line actually was the right situation, which is the medium climate sensitivity, you compensate for the slack you have done before. If you learn that the problem is actually not as bad as you think because the climate sensitivity is low, you relax. But the interesting point is if you learn that the climate sensitivity is high, what has happened in this time that at least in this simple model, you are already beyond the point where you have committed the system to an MOC collapse, at least in the model of Stocker and Schmittner, and you are basically have passed the exit or you're beyond the waterfall. It's a very simple cartoon, and we do not claim that this is a valid description of reality, but it certainly is a twist on an economic model that shows that uncertainty learning has an effect. And where the natural science comes in is to determine when would we learn, and to which degree would we learn. Here we assume, like most economic models, that we remain uncertain, and then at some point, predetermined exogenously from the outside, somebody switches on the light, we have no remaining uncertainty. Of course, that's just one approximation. And so the question is, how does this work? So you can see here that the way you represent uncertainty has an effect on efficient climate policies, at least efficient in this framework, and that if you, in this case, the uncertainty acted to cause a collapse in 1/3 of the cases, which has not happened as the efficient policy if you have certainty. So that's an interesting little effect. Okay, and the details are given in this paper, which is available on the webpage. I would be happy to discuss this. Yes?
Allowed to discuss this now?
I think we should maybe, if there's a clarification question, we should do it right now. Otherwise, we should leave it to the...
I want to remark that there is an economic literature on option value, which I think would indicate a different policy in some circumstances.
We solved the full economic optimal growth model, which the option value is actually in there.
Yeah, I'm not questioning what you did. I'm just suggesting there must be a difference then between that and some of the other problems where essentially you learn more about the system and therefore there's a value in maintaining more options than you otherwise would.
Maybe you've been the reviewer of the paper, which I have been forced to. I actually have to learn about option value quite a bit, and more than I actually wanted to. And there was a one-page discussion. It turns out that if you solve the full economic optimal growth model, it pops out of the solution. You don't have to, the model does the thinking for you here, which actually it shouldn't do, but you get a solution, you think about the solution. But it's a good point. Okay, challenges. What are challenges from my point of view? This is a selected list, highly biased, but still, number one, detection may, I actually should do this the other way around, but what the heck. Detection might occur after the threshold has been triggered. Now, that is something that has been pointed out previously by Ben Center, who wrote a very nice paper in 1995. So it's actually 10 years after Ben Center's paper. And this is a question that, from some point of view, I think, might merit some closer attention. The second one is interesting. If you think about detection and say, well, let's design a better system, you have to face the challenge that detection and prediction depend on random errors. And hence, the detection time at which you can reject the null hypothesis are random variables. Which also means that you have to think about reliability of a system and in a very engineering concept of how reliable would you like to have the system to be. And you have to think about how decision makers react to this uncertainty in the detection process itself. Third, that's something which, it is somewhat humbling to give a talk in front of Carl Wunsch because it always is, but no, it is because he wrote a paper in a journal called Oceanography, I think, where he looked at this and he said, well, what's the one with Peter and Paul? Yes. And that it requires information about unforced variability. And I think it's a somewhat, not dirty little secret, but it's something typical detection studies assume we know the variability and in reality we don't. And that will introduce a few interesting twists, which we'll talk about more in this. And I just wanted to outline it. I'd like to make a second iteration on the issue of overconfidence with some examples, with some numbers, and because I think we have seen potential examples of overconfident analyses even in this workshop. And this is something we have to face, especially if you care about the outer bounds and the outer ranges of the distribution. And then finally, for some decision-making frameworks, it is prediction that is required, not detection. And it seems to me intuitively obvious, this is a nasty word, one might conclude, and this hasn't been tested, but I think it seems to be obvious that prediction, not detection, is required, and prediction is actually the tougher issue. So what I would like to do now is to run through, give you some feedback on those, and then suggest a few potential approaches to at least address one or two of those challenges. Question?
What about attribution? Is that you putting that in?
Yes, because if you do right protection, Freud. If you do correct the appropriate efficient prediction, you have to have the mechanism right. Okay, so same picture as before. We have seen this before. Detection might occur after threshold has been triggered. Picture by Kubash, which we've discussed before. And we've seen this before. I just want to say, in sensitive models, the one for a number of reasons where the MOC actually might have collapsed or crossed the threshold, the collapse might occur on a timescale of 100 years from now. Detection in some studies like Ben Center et al. Occurs after 120, 130 years. And if you want to do something about it, you have to do something before you've crossed the threshold, which you should do something here. So the problem is that the blue error is behind the green, and we have to move the green error in front of the blue in front of the green, because we have to know something before we start to manage, at least if you want to have a somewhat efficient strategy. And you can do this by many ways. What we have done in a very simple way, we have used the GFDL 1994 time series by Manabe and Stauffer and did a very simple Bayesian detection analysis where we analyze the problem if you have infrequent observation and observation error. Because that's the reality. You don't have the luxury of observing each variable you have in a model with 100% without observation error. And to no big surprise, if you observe infrequently and with large errors, you detect later than when you observe often and with high accuracy and precision. If you think about the decision time around 75 years, which we get from an economic model as a rough first-order approximation, then to be in this region, you have to observe much more often than every 20 years, roughly on the timescale of 5 years and on the order of 3 to 1 square drop. And again, it is humbling because Carl Wunsch wrote in the same paper, if you want to stay on top of the ocean observation, we have to go out roughly every 5 years, not every 20 years. So what Carl did with his intuition, when was the paper published? Yes, almost a decade ago. Now we have done with quite a lot of work, but at least we have those interesting curves. Well, okay. And of course, there are many caveats. It's a single MOC model, simplistic foreseeing, and interesting enough, what we show here is the median based on 100 Monte Carlo runs. And if you look at the PDF of the time of detection, which is, yes, I'll discuss this right now. Okay.
I just wonder what the axis meant.
Here?
Yeah, detection.
Yes. This is the time at which, when you have a prior of 0.5 for sensitive and insensitive MOC.
But it's time for present, right?
Yes.
Yeah, so 75 years.
Yes.
Years.
Oh, years. Sorry. Let me write this down. So 75 years from beginning of the foreseeing in the simplified model of Manabe and Stauffer, you would be able to reject in a Bayesian framework from an 0.5 prior to 0.95 prior in the correct hypothesis. And you can play with priors and you can play with observation error. This is a very simple model and we do not claim this to be the final. And interesting, the purpose of this calculation is insights, and if it gets the same conclusion that actually by intuition is told to you, then I think it's interesting, and you can now say, well, if you want to do something here, maybe you want to do it on an annual scale. And this is what Johanna Beers is going to talk about. How do you do it if you want to do it on an annual scale? What's the observation error? And the main point to take away from this is that if we were to continue the hypothetical current observation, the current observation system, or one interpretation of every 20 years with a Vos-like effort with 2 to 5 spheres of uncertainty, we wouldn't get there. We need to be out more often if we think that detection is something we want to achieve. The second point, I think, is somewhat deeper. And that is because the observation is a random variable, we don't know which world we live and whether we have an evil deceiver which gives us observation error just to really have a late detection, or by dumb luck we have early detection. The detection time has a PDF, and we could do more of those. But the 75 years which you designed for is the median here, but we could detect in 30 years or in 110. And so if you want to detect with some reliability, which means 90% of our cases or 95, well, then just plot the CDF, put a constraint in it, which means that you have to be out even more often than that. So so far, this is nothing fancy. Yes?
You devised your detection criterion ab initio, so you're using a fixed detection criterion. You haven't considered the problem then of adjusting the criterion to provide some sort of...
Oh well, in the paper we go into this to a large extent. Right now we want to keep it very simple and very easy, and so we say 0.95. Of course, to come back to the tiger, the false alarm likelihood in an economic, in a risk-neutral decision maker is a function of the cost-loss ratio of the decision. And if you have to make assumptions about the damages, and if you do those, and we do this actually in the paper, then you have to take back 0.8, not 0.95. But this is something, before, to be honest, we had this paper in Snowmaze 3 years ago, and we actually had a grandiose optimization where we optimized the observation period with uncertainty. Bullshit. You have to have what can you say? Orders of magnitude, simple conclusion, 20 years, 5 startup doesn't get you there. 5 years might get you there, but careful, you have to plan and you have to account for the fact that it's a random variable. And so if you have a degree of risk aversion and you want reliability, then you actually have to think about the decision process. And so I'm glad you raised this here, because what decision-making criterion is applied? For what should we plan? Should we plan for expected utility, risk neutral? Then this doesn't make any, then this is fine. Do we do risk aversion? Do we do robust decision making? And this is why, this is one of the topics that is addressed by Gary Yoer and Rob Lampert on different decision making criteria and how this might work out. And so I think that's the logic behind the a few of the speaker lists in the third session when we talk about decision making.
Clarification question.
Yes.
Why are you using MOC and not droughts in Africa or anything like this?
This is very general, and we can do this
can hold for everything,
yes.
right?
Yes, we in the paper it is point hypotheses about fingerprint detection and cost-loss ratio. What you assign as cost-loss ratio, and it's fine. The paper is on the webpage. It's submitted to Climate Journal of Climate. So yes, it is designed as abstract general, but we apply it to a specific case because you make I think a stronger point if you think about first develop the theory and how would you think about this and then go on. Okay, fine. And here the issue comes in, well, if the detection of the pure MOC signals are difficult, are there other fingerprints we could use? Which is, I'll talk about this in the few other slides, but this is where Richard Wood comes in about detection of fingerprints and multiple fingerprints, and also Johanna Beer to some degree. Okay, and now, again, this is an example. We have seen a few example time series. This is my simple example of a time series. I label this here in Sverdrups and year of observation, but it's a fake data set. Something produced with 3 lines of MATLAB code. And assume this is an observation you would get. Okay, we had an implemented observation system. Assume even that the observation error would be 0. We get this out. What would you conclude? Well, I go back and I take my glasses off and I say, well, it looks like a slope. It looks pretty convincing to me. And if I show you the full time series, which is the right, where the left is a subsample, and I tell you this is a full time series which is stationary with a high AR1 persistence parameter, this is nothing fancy. This is more or less a didactic ploy. But the point is, if you don't know the past, then we cannot interpret the observations. And assumptions about this rely on, right now, on model representation of natural variability and their persistence parameters and autoregressive parameters, which is very unclear. So to make another example for ENSO, right, there are many papers, there's a stack of paper that big, at least on my desk, about ENSO change detection. And you can actually divide them and they say, yes, we detect, no, we don't detect. Depends on the structure of the time series you assume. It depends if you allow for model uncertainty. And it depends also on the question whether you allow for, whether you use the data twice. Once to get the persistence time series, you look at your data, you say, oh, AR4 looks fine. Then you, by magic, forget that you have used this information already, use this again, and you have data mining problems. So that's something which is a real challenge. And of course, this is a time series constructed with a very high persistence parameter. Let's use a time series, this one here, which has the same persistence and AR1 properties than the MOC in the GFDL model of Manabe and Stauffer, 0.65 positive persistence. We use a time series. This is 0 trend. And we use a Bayesian inversion of a slope, intercept, and a persistence. And if we assume a priori, if we assume a priori, we know the persistence, which is the correlation between the first and the follow-up for basically between 2 points in time of observation, if this would be 0, then the 95% confidence limit of this inversion excludes the 0 line, and we say, oh, we have detected. This is what you get if you look at this time series. Well, it looks like a slope. Of course, if you have to estimate also the persistence parameter and here's the reality, then believe me, the maximum likelihood actually is close to here. And then the PDF, if you project the probability mass down to the slope, well, it includes the null hypothesis, and you cannot reject. And this is actually the simplest case because we have no observation error. We know the structure of the time series. So this is actually, we just done the easy part. So this is one of those challenges that means that even if we have 20 to 30 or 40 years, it takes quite a long time series to get there. Or you have to have, and here we come back to, I think, one of the themes of the session so far, you have to have good information about the past on a time resolution comparable of your observation time, which means likely annual or on 3 to 4 to 5 timescales, which becomes very tough because you have a kind of filtering in there when you go back into your paleo record. Okay, fourth. And I chose this example, there are many other examples, I chose this example because of the relevant location. Every year, for the last 10 years, there's a meeting in Snowmass from the Energy Modeling Forum. And Draper, who is a statistician, in 1995 said, well, let's look at the oil price predictions of those models and plot them. And so you plot here the oil price in some unit, dollar per barrels, over a year. Prediction is done around here. And you look at the spread of the models. And he did this in 1995, which is here, here. And you can actually use the data. And lo and behold, the reality is outside. This is close to what you asked. Well, what's the skill of those economic models? If you had chosen the range of the models as a realistic bound of uncertainty, and then you would have been extremely overconfident. I'm reminded of the situation when the uncertainty about the oceanic carbon uptake was 2 plus or minus 0.8 gigatons carbon per year. And this was the range of 2 model simulations in one of the early IPCC cases. Of course, we have gone a long way since then, and we have now different ways to do it. But I think it is a simple case to make here that overconfidence is a real potential pitfall. And if you are concerned about the tails of distribution, you're not going to get them by modeling a comparison. You have to have data to confront the models with. And that this is not just an irrelevant example, that there's actually some relevance to it. Well, you can show here because those models predict business as usual CO2 emissions because the oil price is derived from a full model here. Here is an example from Mike Schlesinger and Natasha Andronova in the paper where they say, how does the uncertainty of the climate sensitivity change over time when you use observations up to a certain time period? So you have the instrumental record, 18-something to 1940. You look at an objective frequentist approach of analysis. Sorry. And you get, 26 to 1.4, humongous uncertainty. And the more information you get to the problem, the tighter the error bound gets. Makes sense. You get this from a Bayesian and from a frequentist point of view. A little bit interesting is that if you have a frequentist approach, that the error bounds actually go up. That's an indication that there's trouble brewing somewhere in your model, in your underlying assumption. Basically, your model structure is a little bit off. Let's put it this way. There's potential that you might want to revisit your model structure. Yes, this is the temperature increase for. It's a typical definition of climate sensitivity, as defined in Andronova Schlesinger in JGR. As the upper bound, if you only have data until 1940 and no paleo prior. Okay? And on the left is the result of what I get when I go through my stack of papers of climate sensitivity. I take just those which report 90% confidence limits, and I plot the range of the confidence limits over time. And I was saying, do we see that? No, we don't. And we see it increasing. And so a problem where you have more observations and the uncertainty increases, something is wrong.
I thought the initial uncertainty was between 2 and 4 because of the topology.
No, this I said the carbon uptake in the ocean. This was a different example. And you can take the IPCC and you can argue about interpretation. There are a few paleo constraints here. This is Antonova Schlesinger. This is Forrest, I think, and I have the literature references there. You have this curious reversal of the expected trend of uncertainty that would happen if you have a correct model structure and correct prior. And this suggests to me that one, you don't know what is going to increase or decrease. Certainly we won't, hopefully not cross the zero line. And statements that it goes to infinity and beyond, quote, we just forget. But the question is it going to increase or not?
Yeah, but the current state of knowledge isn't that there's 95% chance or whatever that is of being 9.5.
Well, careful. I try to choose my words carefully here. I said I use the papers and reports what they write. What you say is the current state of knowledge is a different thing. Get peer reviewed and I put you in.
Yes, but the current state of people's knowledge is not that it's not.
People's knowledge? How do you measure that?
What do you mean by
Let's
that?
look at the IPCC report, for example.
Well, the IPCC report is one is here, yes? 1.5 to 4.5
Yes,
interpreted.
these later ones are not using the full information, which is...
Actually, the later ones are claiming that the people who the IPCC report was not particularly careful what they meant by the upper and lower
Yes.
bounds, and if you do it more carefully, that you in fact get the much wider bounds.
Yes,
and
and Dick-
that is the claim.
Dick, weren't you writing one of your pieces and then there was the discussion, there was a piece by Michael to you?
Michael had some different viewpoint.
Okay. So let's put it this way.
On the left-hand side is the same as on the right-hand
Yes,
side.
precisely. That's important. And so this is not, look, this is intended to wet the whistle, to get us going, and to show a few of the issues that are challenges. I'm not claiming I have solved this problem, I want to point it out. And since I am not...
left-hand side
Let's just finish my sentence,
including
please.
more and more
And since I have
information
not...
as you go along?
Okay, go on.
Is the left-hand side supposed to be including more information
Yes.
as it goes along?
Yes.
Well, the right-hand side is not including more information as it goes along.
Why?
Because
Sure it
those
It is,
Antonova and Schlesinger were doing a different problem. They were not using all the information that was available.
Well,
See,
let's-
Richard Woody's not going to say.
Actually, I think they're supposed to be using more information in the sense that they
There's-
that we understand what we mean by the boundary, the endpoints, much better than
yes.
than the committee report, and
Yes.
so we're using more information in that sense.
Reflection of the literature.
It's a review of the literature. I'm not claiming to have done any original research here, okay? There's a few in there. We'll get to this. So if you want to criticize me, do it for the things I've done, not the things I'm just reporting. Touche? Okay, fine.
It's a misrepresentation.
Okay. I know who I will contaminate as reviewer. Next simple, and this is a summary of toy problems. There will be serious work, but more towards the end of the talk here. Oh shoot. Very simple. We use a simple box model. Don't get me on realism. And we force it with a simple scenario. And we look at the MOC response if we superimpose a simple AR1 error structure. And with low, medium, and high sensitivity, we get either a collapse, no collapse, weakening, weaker weakening. And the point I want to make is very simple. Detection is the problem from this band future to one of those. We can get there in 100 years. Prediction is to say, are we going to be in this basin of attraction or in this basin of attraction in 150, 200 years? And that is something which we're not going to get in 100 years, which is much tougher. And if you want to do prediction, then all the analysis we have done so far on detection design, which there is now again a stack of 5 to 6 papers, it's interesting as a first step, but again, we've just done the easy part. Okay, so enough bitching. How can we do that? And I'm not saying those are approaches that might work. One approach is the following, and I think that's an extension of what Richard Wood did and what many people did is, maybe there are hydrographic tracers which have a higher signal-to-noise ratio than just the maximum of the MOC at 25 north or 26 north. And so what we plot here is, in the model simulations from Mathieu et al., maximum MOC at 26 north from 1880 to 2100, and you see.
What you mean with prediction? Just define the term technically.
Okay, with prediction, I mean for this case here.
No, the way you use that word.
It's a derivation. Okay, don't quote me. It's a derivation. My interpretation is a derivation of a PDF of a future outcome of a system.
And what is the dice which is rolled, which is determining the PDF?
This is the infinite amount of parallel universes. No.
I mean, this is important now.
Yes.
I mean, what emissions are? Do you obviously you predict emissions yourself, also, right?
Yes, to some degree. Yes. Yes.
So
this is
they are predicted, the emissions here.
Yes, there are. You can do this in those economic models, and
But you make certain assumptions, right?
yes, and we
So how many Chinese are living, for instance?
yes, and this is one. Okay, this is one scenario here.
But you said prediction. You didn't say scenarios. So I just want to know what that word means.
Okay, prediction means you take the observations you have so far, you take the family of reasonable models that you subjectively have chosen, you calibrate them, get the PDF, do an appropriate Bayesian weighting of them, go forward and derive and...
Do you mean with PDF a frequency distribution?
No, the probability density function.
Yeah, then I have to ask what the dice is. If you say probability, then I ask for the dice.
Okay, let's do the easy way out. Let's do the
subjective.
Subjective way informed. It's the update of the subjective prior updated by the information. Well, we can get more into this detail.
Still do not understand it. Sorry, I mean this one is obviously pretty important.
Okay.
And I don't understand that so far. I think it's a bit mysterious what you say. I thought I have some understanding of it.
Yeah, I have no problem with that. Okay, so we should go...
If you say it's a scenario, then I have no difficulty. But if you say it's a prediction and you associate a PDF, then I'm in trouble. Because I do not know what the dice is, as you said.
Okay.
I mean...
Shall we go? Okay,
well, I mean, you're asking what a subjective probability is.
I mean, if you just say, it's very likely that I'm not sure, that you
Hans,
become 80 years old or something. No, that's the objective.
Hans, I have said that is the update of the subjective probability informed by prior. So it's a Bayesian updating information. So I fulfill all the three axioms of probability. Okay.
Are you assuming equal probabilities for the various models that you?
No, this is what I said.
You don't put
I said a priori I can. We're getting technical here. It's good. What I'm saying is, my interpretation is, a priori, if I have no information, I claim ignorance. I do Laplace principle of insufficient reason equal priors. As soon as I have information, it's a dangerous thing to do, I know, but it's one approach. As soon as information, I can weigh the models that are there, which are of course a subjective choice and a subsample of reality, by how well they're doing in the future. It's the same way for example, how well they've been doing in the past. So models that do poorly with respect to reproducing the reality have a lower likelihood function.
That means you're predicting the economy of the past 100 years in these models?
That is one claim, yes.
Well, you must do that, otherwise it will not be fair.
Yes.
And these models do that, so you predict...
You can totally get out a number.
No, but I just want to make sure.
Yes.
The models you're speaking about include an economy. They have been used to predict from the year 1900 onward what happens in the year 2000, right?
Yes. Yes. And whether this is economists are...
I understood.
Okay, so we're on the same page. I'm happy now. You're the next speaker, so I sit in your chair.
I just wanted to know what...
No, we're fine.
I suppose comments on it.
Okay, so prediction is tough. There might be fingerprints. One fingerprint is oxygen in deep North Atlantic. And I hope Hernan will talk about whether we actually see trends and what's the uncertainty. This is a model. You can certainly argue. The point here is that there's a mechanistic link, important here, mechanistic link between deep water formation rate and oxygen, or AOU, which is a derived tracer. And if you have a mechanistic link, and you have a better signal-to-noise ratio, you can do tricks with fingerprints and maximize signal-to-noise ratio. You can play the games of optimal detection. And so that suddenly makes the problem of detection less daunting, potentially. Many questions to be asked. What's the observation error? What's the realism of the biology which plays in here? What's the... But models that have different response of the MOC have different response of oxygen and other tracers. So there is a potential way to look at more tracers and have multiple sources of information. Simple Bayesian approach. And here is actually where real work comes in. This is work in preparation where we have said, well, do we see the trends? What this is the model fingerprint between the 90s and the 70s in the Martyr et al. Model in the Southern Ocean. 20 micromole of oxygen.
Could you say again what you call a fingerprint technically?
Okay, what I'm saying, forget fingerprint. This was fingerprint combination. Here is pattern. What we use here is the pattern of oxygen changes.
Between 2 decades.
Between 2 decades, 70s minus 90s. And this is the data. Roughly 80,000 data points going there. And now the question is, do we expect Martyr to have the perfect model? I wouldn't say so. Do we think this is similar? Well, we can do statistics and pattern correlation and everything. But we actually see some indication that it would be similar. And the question is, how does this look like in the North Atlantic? And would this be useful information?
So O2 is just a function of MOC?
No.
It's a function of biology, it's a function of biology is a function of winds and nutrients. And
all of which are represented in those models. And I said there's a mechanistic link. I not said there's a unique invertible function.
Okay, so it's not a real fingerprint.
What?
It's not a real fingerprint.
No,
I'm an old person. Speak up, please.
It's not a real fingerprint.
Whoa. So you only, if the model is perfect, you're allowed to be a real fingerprint?
No, it's a proxy.
Yes. As is the MOC we plot here or many other things. It's an imperfect model, yes.
Right. O2 is a proxy for MOC. That's what
no, no. O2 is affected by MOC in some ways where you can put bounds on the likelihood of different changes. So you have to do an uncertainty analysis around those bounds. That's more precise in the clarification? So that's something which is working. So this gives us some hope that we might actually get there. And I'd like to just revisit the challenges and to come to a conclusion. First problem poses a question, how can we improve detection systems? And we're going to talk about this at length in this session. What reliability should one design observation system? This is where we have to talk with psychologists to actually know how decision making occurs and how you analyze this with a sound way. And so we have talks about that. We should really look at the problem of detecting trends when we have no strong a priori information about the autoregressive or other time structure of the natural variability. We have to get out of the mode of saying, we have a perfect model of the past, we have a perfect model of the foreseeing. When would we see it with perfect observations? That's interesting, but it's a lower bound of detection time. And if you want to detect at certain times, we really have to get this assessed. We should think about overconfidence, because it seems to be a recurring pattern. And if we really are concerned about the tails of distribution, then this is something we should be aware of, at least as a concept, and try to find out whether there are ways to guard against this. And we should think about the prediction challenge, whether prediction is tougher than detection. I think this is pretty obvious from first principle, at least it is in my gut feeling. Okay, I think so. But that means we have to think about the requirements of observations to inform prediction, not just detection. And with that, I think I'll close. I'm sorry if I went a little bit over time. Questions? Yes?
There's another way to move those green and blue arrows.
Yes?
And that is
reduce it.
Slow the pace of the car.
Yeah.
Yes.
Yes, exactly. Yeah.
Yes. Yes.
And that might be an easier challenge.
Well, not cheaper. Not cheaper.
You don't know.
You don't know. But, well, we've done a lot, yeah. I would argue that orders of magnitude could get you a rough.
Depends on how you structure the decisions and the degree of confidence of the detection and the decision variable.
Yes, you're right.
How much type 1 and type 2 are you willing to allow?
Rob and Hans.
Yeah, two points. One to pick up on Gary's. I mean, you've very nicely structured this in terms of the thing we want to know is where this threshold is. And there may be other bits of information that are more useful or allow you to set up different kind of decision constructs. For instance, decision makers might be interested if there's some threshold probability of really bad things happening, in which case they're willing to pay the price of slowing down.
Yes.
And so that might be a bit of information which is different.
So I was flipping it too much in my default model structure.
No, I'm just generalizing your point. The second one is the question that Hans raised. I think it's actually much more general and fundamental than I think you answered, which is really the whole question of subjective probabilities. I mean, decision frame. Maybe David wants to say something about this, but
it's nice to have him here.
Decision theory is classic decision theory is framed with states of the world and estimates of likelihood for states of the world. Okay, and where there is where it is a repetitive situation, so one can get frequentist data and say this state is 30% likely and that's 70% likely, then you do that. But decision theorists, at least, are generally quite happy where that sort of information is not available to use the probability calculus and stick degrees of belief on it. And so you go interview 100 experts, or you do whatever you're going to do, and you say, I think this is 10% likely or 30% likely, and there's no frequentist information at all.
Yeah, and I've done this too by having equal likelihood.
Sorry, but
I was honest about it.
Yeah, but that's a fundamental view of what likelihood means. And I was actually going to comment, though I didn't remember the reference, and so in Carl's talk this morning, there's a wonderful little essay in a volume dedicated to James Marsh, who's a famous political scientist. I don't remember his name right now, but wrote an article on how you are arguing from cases of one or fewer. Right, that's what historians do all the time. I mean, anytime it's looking forward is a lot different than looking past, because oftentimes your n is 1 or 0, and you've got to gather up the information you have in some fashion and use it. And I think the third session
hopefully
is going to at least touch on some of those issues.
Hans?
I mean, I think I have to learn here something new. I was among the pioneers of detection business. And so far I understood that we first have to say is what we presently see. I think detection and attribution have to deal with what is going on now. We make a statement about now, not about the future. Based on this decision we make now, we derive some confidence that we possibly can say something about the future.
Not
the detection,
necessarily.
that was my understanding.
Okay.
And so maybe I have to learn something new. And so the detection means, can we really say that we see something uncommon, unconventional?
Okay.
And that leaves us with the problem that we definitely do not know what the national level of evidence is.
Yes.
And we cannot run away from it. There's no way of running away from it. So there remains a subjective element. So if somebody's saying, I do not believe that you have estimated the level of probability correctly, then I cannot disprove this person, but he cannot disprove it if I say I believe it. But it's a matter of belief, simply.
Yes.
Second point is attribution, that we say, okay, with the present models, which we've seen for the time until today, where we know all the 4 things, which is giving us the best explanation of this, what we consider as abnormal. But now you started something totally different. You said prediction.
Yes.
And you said, and I was really surprised about that. I didn't believe that an economist would dare to say so.
I'm not an economist, I can say that.
Yeah, but the economists here, they didn't attack you, so that was
We were doing a fine job.
That you say that you can make economic forecasts on timescales of 1 or more centuries. I was surprised to hear that. And so obviously if you say, I'm
implicit in the
since I can predict without external parameters, without parameters I do not know now. I can predict, in the year 1900, I can predict what happens in the rest of the 20th century without having any data from the 20th century. Only that would qualify to say I can make a statement prediction of the 21st century. So you cannot bring in the fact that you found out that suddenly there's something like an internet or the Soviet Union came.
But you don't have to predict the internet. You have to predict
I understand that you don't.
A broad range of CO2 emissions, which is bound by
Anyway, so you predict the emissions. You said that you predict the emissions.
Yes.
In the same way, so it's in principle no difference if you're in the year 1900 or now. Yes. The only difference is that you can look after if you really hit it. So that's something I learned, and this would mean that the whole concept of scenarios which you have used so far is no longer required. Because the scenarios have the idea of we cannot assign probabilities, we just can tell stories. And the stories are meant that we discuss then, what do we do if this really happens? Can we deal with that? So that's a fundamentally different thing. And if the economists are so good at doing that, I must say I'm excited, and I would say this is significant progress. I'm sure that
this is a faint praise or loaded question.
A big article about it, because it would really not only solve the problem of predicting climate, but also economy to some extent, and that would be something. Which shares am I supposed to buy?
Yeah, Gary's selling shares this afternoon.
Yeah. So that's what I understand. I'm just,
thank you for your praise. I'm really not sure how to interpret it.
When he makes his prediction of which shares you should buy, will you follow his advice?
No, because everybody else will follow.
Oh, okay.
I think with that, being the chair of the session, I think we'll now switch gears and let Hans van Storch talk about.
But it's boring what I'm saying.
About
I'm not predicting.
Prediction.
Yeah, whatever.